This is about indeterminate forms. So, first of all, what is an indeterminate form? Let me tell you. So, let me ask you an easy question. If I have two functions, f of x and g of x, and I know that the limit as x goes to 2 of f of x is 3, and the limit as x goes to 2 of g of x is 4, and I ask you the question, what is the limit as x goes to 2 of f of x over g of x? Well, I know the top is going to 3, and I know the bottom is going to 4, so if I do f of x over g of x, I just get 3/4. That's no problem. An indeterminate form is a similar question that isn't so easy. What if I have, and this is like the same thing except now I'm saying f of x goes to 0 and g of x also goes to 0, and I ask you the question, what about f of x over g of x? Well, this is like 0 over 0, which is, we can't just do 0 over 0. We can do a lot of limits where the top is approaching 0 and the bottom is approaching 0, but 0 over 0 just isn't a thing. So I can't just say the answer is going to be 0 over 0. That's not an answer that makes sense. In fact, this, I would say the answer is that we don't have enough information. The information that we're missing is, roughly speaking, how fast does f of x go to 0 and how fast does g of x go to 0? Like, we have this picture of f of x being a really small number close to 0, g of x also being a really small number close to 0, but it makes a big difference which number is smaller than the other one. So I'm not going to get a good answer for that. There's no general answer that I can give you. It's different in every case. And we've seen plenty of examples like this, say in Calc 1, just to remind you, here's the limit as x goes to 2, and if we check, plugging in 2 on the top gives me 0. Plugging in 2 on the bottom also gives me 0. So this is an example of the situation I was just describing. We're doing the limit of a fraction where the top goes to 0 and the bottom also goes to 0. Of course, this is like some of the earliest limits you would have done, where we're going to factor the top, factor the bottom, cancel something, and now try again. After canceling this, the top goes to 5 and the bottom goes to 4. And for that, we have no problem. I just get 5/4. So they're not all so easy. It's possible to have a fraction where the top is going to 0 and the bottom is going to 0, but maybe it's not polynomial, so you can't factor it, and that there's various other problems that could arise. So what we're mostly going to talk about today is a powerful tool to deal with such things. This is called L'Hopital's rule. Suppose f and g are differentiable, so the derivatives exist, and we're going to suppose that g prime of x is not 0 on some open interval containing a. Yeah, I am missing a piece of information here. Except possibly at x equals a, but it's not 0. In some interval containing a, it's allowed to be 0 at a. And let's suppose that either f of x and g of x both go to 0, or that they both go to plus or minus infinity. So like f of x could go to positive infinity, g of x could go to negative infinity, or any combination of positive and negative infinity. Then when I try to do the limit of the fraction f of x over g of x, that's going to give me the same answer as if I did the same limit but with f prime over g prime. Assuming that this other limit actually exists, and when I say it exists, that includes the possibility that it could be infinity or negative infinity. Also, this rule still applies if a is infinity or negative infinity. That's the number that x is going to. Okay, so how do we use this? Let's do the same example again, but let's use L'Hopital's rule. First of all, I need to make sure that when I'm looking at this fraction, I'm in one of these two cases. Either f of x and g of x are both going to 0, or they're both going to plus or minus infinity. This is the same example we just did, and we already know that the top and bottom are both going to 0. I'm just writing that again because that's justification that we're allowed to use L'Hopital's rule. So let's use L'Hopital's rule. I take the derivative of the top, the derivative of the bottom, and now that's my new limit. And now I have this to deal with. And I can just plug in 2. If I plug in 2, I get 5 on top, 4 on bottom, and so I have no problem. And of course, that's the same answer we got doing it the other way. So that's your basic L'Hopital's rule. So an indeterminate form in general is when you have typically two functions and you know how each function behaves, like maybe f of x goes to 0, g of x goes to 0, or maybe infinity or whatever. But what you're interested in is a limit that's like a combination of f of x and g of x. Like it could be f of x divided by g of x or f of x multiplied by g of x. And it's called an indeterminate form because simply knowing what happens to f of x, like whether it goes to 0 or 1 or whatever, and knowing what happens to g of x, does not necessarily tell you what happens to this combination of f of x and g of x, whether we're talking about f over g or f times g or whatever. These are called indeterminate forms. So 0 over 0, when I write that, that means that we're talking about a function that goes to 0 divided by another function that goes to 0. We're not literally talking about taking 0 and dividing it by 0. We're talking about a function that goes to 0 divided by another function that goes to 0. Similarly, infinity over infinity, that's another indeterminate form. And when I write infinity over infinity, I include, like, infinity could mean negative infinity. I'm not, when I use this notation, I'm not distinguishing between infinity and negative infinity. So these two things are exactly what L'Hopital's rule is for. Like, these are the two cases of L'Hopital's rule. This one's 0 over 0. This one's infinity over infinity. So if I get one of those two, I just plug it directly into L'Hopital's rule. Then there's more indeterminate functions, and I'm going to tell you what to do with pretty much all of these. With the rest of them, we can't necessarily use L'Hopital's rule directly, but I'll get into these. But for now, I guess maybe let me probably finish this video with an infinity over infinity form. This is the same function, like we were doing the limit as x goes to 2, now I'm doing the limit as x goes to infinity. So as x goes to infinity, the top goes to infinity, and the bottom also goes to infinity. So this is an infinity over infinity form. And it's important that I write that because I'm about to use L'Hopital's rule, and L'Hopital's rule only applies if it's a 0 over 0 form or an infinity over infinity form. So if you use L'Hopital's rule, I want you to write something like this, just indicating that you checked that L'Hopital's rule actually applies. So I take the derivative of the top and the bottom. And by the way, let me mention something. When you do this, you're not using the quotient rule. Like, I'm not doing the derivative of the entire fraction. I'm separately doing the derivative of the top and the bottom. It's different from the quotient rule. It's easier than the quotient rule, in fact. So here we are. And now I look at the new limit. And the new limit is still a bit of a problem. As x goes to infinity, the top is still going to infinity and the bottom is still going to infinity. So sometimes we do L'Hopital's rule multiple times. Now the derivative on top is just 2, derivative on the bottom is just 2, and now we have an easy limit. This is just 1. So that does happen sometimes. We use L'Hopital's rule multiple times. Of course, there's a shortcut to do this. If you have a polynomial divided by another polynomial, you can basically ignore everything but the leading term. So the leading term is the one with the highest power of x. So if I just look at this as x squared over x squared, of course I'm going to get 1. But the work that I just showed you applies even if it isn't a polynomial. So that's your basic L'Hopital's rule. We did a 0 over 0 form, an infinity over infinity form, and I am going to tell you what to do with the rest of these in the next video.